Good afternoon. So today we're going to finish up sorting, and we're going to go over several examples of comparing the selection sort and the merge sort, but in particular, we're going to be comparing them based on how to cost, in a very rough sense, how long an algorithm takes. Okay, so we're going to use the big O notation in order to say, okay, this algorithm is big O of, say, n squared. This algorithm is big O of n. The big O of n is more efficient than the big O of n squared in principle. Okay? Now, I'm also going to outline a 4-step procedure for how you cost an algorithm. And it's very important to pay attention to the form of it, because I've learned from experience that if I don't present this 4-step procedure, it's usually very difficult for students to solve the problem. So I've outlined 4 steps, which is all I'm going to ask of you to do to cost an algorithm, and usually those 4 steps are fairly straightforward. Okay, so let's begin. Let's just recall selection sort. So again, find the min over all the elements, swap it into place, then find the min over the remaining elements, swap it into place, and keep going until you've gone through all of the elements. Okay? So let's recall the cost. Remember, I color-coded the cost so that we could see how the terms are grouped together. I would give you the formula, which is the sum of the first n numbers is n times n plus 1 divided by 2. And then the rest of it is just follows through from the previous line. And we ended up with this idea of n squared over 2 plus 5n over 2 minus 3. And the key is not to pay attention to the details. The key is not the 3 or the 5n over 2 or even the n squared over 2. Really the important part of this expression or of the algorithm is this big O of n squared. And remember, what this means is that if I were to double the input size, I would effectively quadruple the amount of operations that I'm performing. Okay? So that's pretty bad. Or if I have a list of, say, 1,000 and I go up to 10,000, it takes 100 times as much effort. Okay? That's what the n squared is telling you. So here's a little bit of code to do the job. So again, I think I took this code from your book, but I've replaced the ints with size t. And remember, why do we use size t? We use size t because that is the more cross-platform way to index elements in a vector. This is more or less saving you from very subtle bugs that can occur on runtime with very large vectors. And they might occur on one system but not on another. So size t is the robust way to do this, and it's an effortless sort of replacement. You just replace int with size t. Again, the reason also is because we're not using any of these size t variables in arithmetic as anything other than just indices in the indices for the vector. Okay. So let's see, what is it? Okay, so what we're going to do is we're going to get the position of the smallest element in a vector range. Okay, so it's the idea of it's not just about inputting a vector. You input a vector, and then you input a range of values for which to search, and then it finds the minimum in that range. Okay, so and you loop through, and you start at the first element and the last element. You find the min, you swap it into place, you increment the from plus 1, and then you basically this is just the first part. So this just finds the minimum position for a given input size. And what we do is we put that in a loop. Okay, so the min position just gives you the min position of the current minimum in the phase. Okay, so if we go back here, if we call min position on, say, from, say, here to there, then it figures out where's the index of the 11. And if we do it from here to here, it figures out the index of the 12, and it returns that index. And then we put that inside of a loop, because for the selection sort literally is just a loop which says, for size t next equals 0. So starting at, next is what we're going to input for the index. Starting at the list of all of them, find the value of the minimum index, swap it into place. If it's not already in its current position, that's what this means. If min position is not equal to the current, index next, then don't do anything because it's already swapped. Otherwise, swap it into place, and then increment next to the next value, and then call it again, and then keep doing this. Okay? So it's just a loop, really. Okay? It's very simple code to write and easy to read. Okay, we're going to hold off on costing. Well, we already costed it, so let's do a different form of costing. Okay, so let's do a very simple version of costing, which is the following. It'd be hard to cost that algorithm, the selection sort, based on the code. Okay, if I told you the algorithm, it's easy to think about. If I just showed you the code, it'd be a bit harder. So let's warm up to this. Fibonacci, right? So with Fibonacci, you start by initializing the values. I guess, I have my initial conditions wrong. This is an old version. So if n is less than or equal to 1, return n. And then otherwise, we start the chain at 0 and 1. And then everything works as usual. Okay? So each of those initial steps is, say, costs one operation. Okay? So you access this element in memory called fold. You have fold 2. You have f new. Okay? Just say each of those operations, it costs 1 unit of time. All right? Or one operation. Now we've got a for loop. And within the for loop, so let's forget about the for loop for a moment, each one of these is, say, 2 operations at most. Right? Let's just say 2. Let's say each line takes up 2 operations. Okay? Now the loop runs n minus 2 times. Okay? So what we have is something like n minus 2 times 2, right? Plus maybe like a 3 from above, or a 10 at most, right? But again, 3 times n minus 2 plus 10 is still just big O of n. Okay? So again, we get to wash away, we don't have to think about the initial step. You see the initial step? It took 3 or 6 or 10. It doesn't matter. Okay? The loop is what is tied to the input parameter. That's what's going to determine how fast the algorithm runs or not. And in this case, the loop is only running n minus 2 times, or roughly n. Okay? When n is a billion, you don't really care about a billion versus a billion minus 2. It takes about the same time. Okay? Similarly, if it's 6 operations or 12 operations or whatever, it's not growing with n. That number of operations inside of here is fixed. It's a constant. So you're really just running a loop n times. Okay? So that's where the big O of n comes from. Again, you can make this precise. You can say the first line takes 3 operations, the second line takes 2 operations, the next line takes 7 operations, but it all gets washed away in the big O. Okay? Now, how would you do recursive Fibonacci? With recursive Fibonacci, right, to compute f of n, you have to compute f of n minus 1 and f of n minus 2. But then to compute f of n minus 1, you have to compute f of n minus 2 and f of n minus 3. It's getting a little bit messy. So let's come back to this one a little bit later. And instead, let's go to the next level of difficulty, which is merge sort. Okay? So Fibonacci, non-recursive, was big O of n based on just one simple for loop. We're good. Okay? Selection sort had a nested for loop. It had a for loop inside of a for loop. And that gave us our n squared type pattern. Okay? Now with merge sort, we still have recursion, like the Fibonacci recursive, but it's a more manageable type of recursion, and we're going to see exactly how to handle it right now. Okay? So we saw that selection sort was big O of n squared. Now let's recall the merge sort, which is, okay, you want to sort, say, this collection of objects. You split them into 2 halves, sort the first half, sort the second half, and you merge the 2 halves together. Okay? So this idea is fairly straightforward, which is, oops. I guess it's on the next slide. Okay. Sort the first half, sort the second half. That's a recursive style of thinking. We want to solve the problem on a smaller number of objects. So the only real wild card here is the merge. And that was what we went over at the end of last lecture. Okay, so let's rethink the merge again. Again, all we're doing with a merge, you give me two lists, and I basically take the smaller index of the two and put it into a new location in memory, and I just go down the line until I've merged together all of the different lists. This is the slide I was thinking of just a moment ago, which is here's how you cost a recursive algorithm. Okay, so to sort a collection of n objects is the same as sorting half as many objects twice plus merging them. And we went over last time the merge was as 5n, just very quickly, and I wonder if I should go back to it. Let me go through that merge real quick, just to make sure we're all on the same page. And just to emphasize why it doesn't matter whether it's 5n or 10n or 15n. Okay? Okay, here we go. How would you merge? So first, to sort n objects, we first sort n over 2 objects twice, and then we merge them together. Now to merge, you check the first index of each half. That was that chart with the blue and the red, and it was going over to the right. Okay? For each pair, you find the minimal index, and then you put it into place. Okay? So this calls upon locations in memory 5 times. So let's count them. Check this value, compare these two values. Okay, so access this value, that's 2. Compare the two values, that's 3. Write the smaller one into a new location in memory. That's 4. Hold the 5th for a moment. You go to the next one. Again, access, compare, write the smaller one. Access, compare, write the smaller one, etc., etc., etc. So that's 4. And then the final step is copy back the temporary array into the original array in memory. Okay? So maybe instead of 5, it should have been a 6. Okay? But it's not going to matter. Okay? Copy back the temporary array into the original array in memory. I said that was 2 steps. So instead of 5, maybe it's a 6. Let's just go with 5. Okay? So thus, to merge requires 5 times the number of points you're trying to merge. Okay? So again, this 5 is fixed. Doesn't matter how many points you have to merge, there's only a fixed number of operations for each pair that you're going to go through. And there's n total, so it's 5 times n, or maybe 6 times n. Okay? That's the idea. So to merge is big O of n, some constant times n. To make it concrete, I'm going to use the value 5. Okay, so that's where that 5n comes from. So this algorithm is recursive. Okay? But it doesn't mean you can't cost it. It just means you got to be a little careful. And it gets a little confusing. Okay? So we're going to go through this as hopefully as clearly and concisely as possible. Okay? So T of n is going to be the amount of time to merge sort n objects. Not merge, but to call merge sort and actually sort the n objects. Okay? So you break that down, you write it as an equation. T of n is equal to, you assume you know what the value of T of n over 2 is. Okay? It's just like recursion. And you add everything together. Okay? Now, how do you sort one object? You check the size of the list. If the list is of size 1, what do? You just return it because it's already sorted. Okay? So it is already sorted, so T of 1 equals 1. Okay, it takes a constant amount of time to check the size. Check the size. If it's 1, you're done. Okay? So to sort a list of, or a collection of one object takes one operation. This is your base case. Remember that stuff plus stuff and then it goes to nuff? That's your nuff. Okay? So T of 1 is 1. Okay, so here's a 4-step process for doing it. Okay, just focus on the top. All right, so here's the 4-step procedure in all of its glory. Let me come back to the slide. I think I did this one at a time. No, I didn't. I did. Yeah. Okay. 1. Find the pattern. Okay. So note that for a given n, the formula can be written as follows for various types of input. Okay. So T of n is T of n over 2 plus T of n over 2 plus 5n. Okay? Now, the important thing to note here is that it's recursive. It's self-similar. So T of n over 2, you can apply the same formula with n replaced with n over 2. So instead of n over 2 on the right-hand side, it's n over 4, T of n over 4, plus, and then make sure you substitute in the n over 2 times the 5. Okay? So to sort a list of half the size, again, T of n over 2 divided by 2 plus T of n over 2 divided by 2. That gives you the n over 4. Plus 5 times the input size, which in this case is n over 2. This is important. You have to get that n over 2 in that last step. You have to have the n over 4 in the last step. The 5 is being multiplied by the input argument. Okay? That's important. Now what we want to do is try and kind of condense everything into a pattern, something that we can sort of condense this idea in our mind and figure out, well, if we do this, say, 5 steps, what is the sort of formula going to look like? Is there a pattern that we can figure out? Okay, so here we go. We just want to look at T of n. So first of all, let's combine the T of n over 2 plus T of n over 2. T of n is just some number. It depends on n, of course, but it's just a number. So if we do it twice, we just multiply by 2, that number. Okay? So we have to do it 2 separate times. So it's just twice times the amount to sort half as many objects plus 5n. And now, like I said, we have the expression for T of n over 2. Let's plug that in and do this 1 or 2 times to see if we can figure out if after 5 steps can we predict what the expression is going to be. Okay? That's the name of the game here. You want to plug in these smaller versions of it until you can predict after 5 steps, after 10 steps, exactly what the expression is going to look like. So here we've got 2 times, and then for T of n over 2, we plug in that second line up above, and we get 2 times T of n over 4 plus, and then, this is very important, 5 times the input size, n over 2. Okay? Now just don't mess up the very simple, very basic algebra. Okay? And we get this over here. We get 4 times T of n over 4. Okay? Because we have both of these 2's, and they combine for a total of 4. Plus, now this is where we have to be very careful, and this is where students have messed up on previous exams. Okay? Which is, there's a 5n here, and then this is a 5n over 2, which is being multiplied by this factor of 2. So at each stage, we get out another factor of 5n. Okay? That's important. We're going to need that to get the cost right. Okay? The 5, not so much, but the fact that it is the same number here as it is right here. Okay? So we can just rewrite this in a more suggestive format from here to here, which is, all right, let me combine both of these. So this, I've iterated through once, or let's say twice, and I've got 2 times this term 5n. I've got 2 to the power of 2 times n divided by 2 to the power of 2. Okay, I've very suggestively rewritten the 4 as 2 to the 2. Because when you do this a third time, the pattern that emerges is this pattern right here, which is 2 to the number of times you're running the recursion times t of n over that number, 2 to the third, plus the exponent here, 3 times the 5n. Okay? So that's step 1, which is just work out a few of the first few cases to find the pattern. Okay? Then what you do is you write the pattern in terms of a variable k, as if to say, if I did this recursive step, say k times, where k is 5 or 10 or whatever, what would it look like? And it looks precisely of the following form. T of n is 2 to the power of k, if you run the recursion k times t of n over 2 to the k, plus, and then again, the key here is you say you have k of these iterations times the 5n. Okay? So if I had to run this 5 times, I would just plug in k equals 5. Okay. This is usually okay. Pretty much everybody's going to get this step. Now the next step requires a little bit of, it's a little more difficult to conceptualize, just for very non-important, oops, I went backwards. Okay, 3. Now we're going to make a simplifying assumption. This is, everyone always asks, why are you making this assumption? I don't get how the assumption works, or why are we assuming that this is the case? We're going to make our lives easier. Okay? So, we keep dividing the number of objects in half, right? What happens if I have 7 objects? What do I do? I give like 3 to one and then 4 to the other, right? But does that really make a big difference? Not really, okay? Because either they get exactly the same number of elements to divide, or one has one more than the other. And it really doesn't make a big deal, a bit of difference, okay? So let's just assume that n is a perfect power of 2. So like 1,024. That way, every time we divide them up into 2 different piles, they're always going to be exactly the same size. Okay? The key is, and this is what you don't have to show or know, or you don't have to convince me, the theory is going to work out exactly the same whether or not you make this assumption or not. If you don't make this assumption, it gets really messy. If you make this assumption, the answer ends up being the same. Okay? So you make the assumption that you can always divide n by any power of 2 you want. Okay? So n is 1,024, 2,048, 65,536. Okay? Just, it doesn't matter, just always assume it's a perfect power of 2, because at some point, this splitting of the collection of objects into 2 halves is going to stop. It's going to stop precisely after the exponent in that my n is 2 to some power. Okay? So if n is 1,024, that's 2 to the power of 10. It's going to stop after exactly 10 steps, or the exponent. Okay? So the reason we make that assumption is because if I have a list of, say, size 1,000, it's going to stop after 9 steps. But let's just make our lives easier, and there's a value of m that makes n equal 2 to some power equals 1,000. I don't want to think about that. It's not going to affect the overall analysis. So let's just assume we're always sorting a list of size 2 to some power. Okay? We're allowed to make an assumption like that. And the reason is because then what we can do is we can say, okay, let's let m be the value such that 2 to the m actually equals n. Okay, so m is going to be the actual number of steps we need to recurse, or apply the recursion, in order to access the base case. All right? That's the critical assumption we're going to make. Because what this means is, right, we start with 2 to the k times t of n over 2 to the k plus k times 5n. And what we're going to say is, let's let k equal m. Let's let k be that value of m, or be that value such that n is equal to 2 to the power of m. So when we plug in k equals m into the equation above, what we get is 2 to the power of m, which is n. We get n divided by 2 to the m, but that's also n, so that gives us a 1. Okay? And then we get 5 times n times the number of steps in the recursion, or in other words, the exponent that n can be written as 2 to that power. Okay? So for example, take n equals 1024. That's 2 to the power of 10. Your m is 10. Okay? So we get something like this. So n is good, right? We know what n is. N is the input parameter. So we sort of have an answer here, which is, oh, well, it's n plus, well, 5n times whatever m is. So we were asked an answer in terms of n. We should give an answer back also in terms of n. So let's solve for n in m. Okay, so the last step in this 4-step procedure is to simplify. Again, step number 3 is the hardest to conceptualize, but it allows you to go from t of n over 2 to the k to, okay, at some value of k gives me t of 1. Now we get to simplify. So t of 1 is 1, so that t of 1 goes away, and we're left with just an n. So we're left with n plus 5 times n times m. So now we just need to solve for m in terms of n, and then we're done. Okay? M is the number such that 2 to the m equals n. So m is the logarithm base 2 of n. Okay? So just plug in n equals 1024, m equals 10, and you'll see the connection. And this is just codifying it in general. Okay? So the math people in the room are probably like, duh. But, okay, if you haven't seen this in a while, which I'm willing to bet about half of you haven't, you're probably still not even going to get it, even after this absolutely wonderful explanation you've been given. Okay? So just look this over a slide again as many times as you need to get back into the habit of this type of thinking. Okay? So, but I can guarantee you this procedure, this 4-step procedure works quite well. Okay? So this is from past experience teaching the course. So just stick to this 4-step procedure, and any problem that I throw at you, you should be able to follow this procedure to cost it. Okay? So how do we bring it all home? So t of n is n plus 5 times n times the log base 2 of n. And now this is where the big O material comes in, because this is which grows faster, n or n log n? N log n. You compare both of these, they both have a factor of n, but the log n actually does grow off to infinity faster than a constant. So the dominating term here is in fact the big O of n times log of n. So merge sort, okay, do I have this on the next slide? No, okay. Merge sort is provably better than selection sort, all things being equal. Okay? There's some overhead every time you call a function, it adds a little bit of overhead to the computing resources. But assuming that's not an issue, selection sort was big O of n squared, and merge sort was big O of n log n. Which is better, n log n or n squared? N log n. Okay? N log n is much better than big O of n squared. Here's someone had a really nice idea once. I think it was in the spring. And they said, wait a minute, can we do better? What if we took that merge sort and we put it up into 3 piles, right? So rather than just, split it in half and do the recursion, what if we split it up into 3 piles or 4 piles or, okay, so let's do 3 piles and see whether or not it makes a difference. Again, the same 4-step procedure. First, t of n is, well, you're going to sort a third of the list 3 separate times, a third, a third, a third. Okay? So that's where the t of n over 3 times 3 comes into play. Plus, and I just threw in a number like 10n. Okay? To merge all three of these lists together, it takes about 10 operations. Okay? Now, sure, because you check this one, you check this one, you check this one, you put in the min, then you check this one, this one, this one, you put in the min. So instead of 5, maybe it's 10. Okay, fine. Now we do 3 squared. We iterate again. So 3 squared t of n over 3 squared plus 2 times 10n. Okay, I'm not going to work out all the details, but the pattern is 3 to the k times t of n over 3 to the k plus k times 10n. Okay? Now we assume that n equals 3 to the m for m equals k. And okay, so here, again, if I divide the list into 3 halves, or 3 thirds, okay, let's just make the assumption that I can always do that it's a perfect power of 3. That's fine because it's not going to affect the overall analysis. Okay? So we make that assumption, and then when the value of m, such that n is 3 to the m, we get rid of the t of the inside argument. So that's n times t of 1 plus m times 10n. Okay? Then we get n plus 10nm. Now, this is where the magic happens, right? N equals 3 to the m means that m is equal to log base 3 of n. So we have t of n as n plus 10n log base 3 of n, which is in principle better than log base 2 of n, but what do we know about logs in terms of big O? All logs are the same. Okay? So we still get big O of n log n. So this wonderfully fantastic idea of split it up into 3 piles is a good idea, but it doesn't really buy you much more than splitting it up into 2 piles. And it provably so. We're not just using our intuition here and saying, well, it doesn't seem like it's going to do much. No, we actually did the calculation, an informal version of it, and then we've decided, no, the trade-off is not there. You don't get any realistic speed up out of it. Okay? That's concrete. That's as quantitative as you probably need to be, but it's effective. It's effective at not wasting resources, at implementing a solution that's not going to buy you that much speed up, even in principle. Let's do another example, a simpler example, perhaps. Towers of Hanoi. Okay? So with Towers of Hanoi, remember, to solve Towers of Hanoi, you move all but one of the disks, then you move the largest one, and then you move all but one of the disks again. Same idea, right? To solve the problem on n things, you solve the problem on n minus 1 things twice, plus the move to move the biggest one into the final column. Okay? So we iterate that a few times. We look at the pattern. 2 times t of n minus 1 plus 1 is, okay, so 2 times t of n minus 2 plus 1 plus 2 equals ... What we end up with is 2 to the k times t of n minus k, slightly different form, but no more or less intuitively different. And then now we get this really annoying sum, which is the sum of the first k minus 1 powers of 2. This is 1 plus 2 plus 4 plus 8 plus 16 plus ... Okay? I would give you this formula. You see this formula right here? I would give you this. This is a mathy formula. It's not easy. It's not difficult to figure this one out, but I wouldn't expect you to figure that out. This is not a computer science course. I just want to demonstrate these principles so you can focus on implementing them and actually making more tools. Okay? So this is well known. No point in reinventing the wheel for this class. Okay? So I would give you something like this. Now, take k equals n minus 1. Right? That's the value of k that gives us the base case t of 1. Okay, so here instead of m being like 2 to the n, or m being the value such that 2 to the m equals n, again, you're just looking for that value that gives you the base case, that unlocks the stopping the recursion. So that's what we've done here. We said that's the value where k is n minus 1. We literally just plug it in, so we get a 2 to the n minus 1 times t of 1, which is 1, plus, And this is where it gets a little bit tricky, right? There's a k minus 1 here, and k is n minus 1. So in total, that's 2 to the n minus 2. But then we're summing up the first n minus 2 powers of 2 plus the n minus first power of 2. So what we end up with when we sum everything up is we get exactly 2 to the n minus 1. Okay? So the answer is big O of 2 to the n, if I just asked for a big O answer. Okay? And I would tell you, for example, that, oh, hey, the sum of the first, say, n minus 1 powers of 2 is, oh, wait, that's wrong. That's minus 1. I set it right above. Here it's right. And then here it's to the n minus 1. Okay. All right, now that we're warmed up, who wants to try and cost Fibonacci recursive? Well, I don't even want to cost this one. But I'll tell you what I would do instead. What a lot of mathematicians do, and a lot of really just, there's two different ways to think about solving a problem. I want an exact solution, and I want it as quickly as possible. I want an approximate solution as quickly as possible. Or I want sort of an upper and lower bound on where the answer lies. Okay? So these are different ways of describing an answer. And sometimes you have access to one solution but not another. But even though you don't have the answer you want, chances are the solution you can get can tell you information that may be sufficient for what you're trying to do. Okay? So rather than get the exact cost of recursive Fibonacci, let's calculate an upper and lower bound. Okay? So how would we get an upper and lower bound? Well, we say, okay, well, to compute Fibonacci is t of n minus 1 plus t of n minus 2. Now, it takes at least as much time to compute t of n minus 1 as it does to compute anything smaller. Okay? So the larger n is, the more computational resources you're going to have to expend. That's sort of apparent, I think, based on the structure. So rather than costing that recursion, let's cost the lower bound and the upper bound separately, and we know that our actual cost lies somewhere in between. Okay? So for the upper bound, that's essentially the same as the towers of Hanoi, right? You do the same thing on n minus 1 things twice. You add 1. Adding 1 doesn't really do that much to it. Okay? So the upper bound is 2 to the n minus 1, or 2 to the n, big O of 2 to the n. So recursive Fibonacci, at worst, is big O of 2 to the n. That's quite a bit of time. Okay? That would not be a good algorithm to run. Okay? But now you can say the opposite, or not the opposite, or just the lower bound, which is, okay, well, at best, if this was, say, the best we could possibly get is making an assumption that's pessimistic. What is the best we could possibly get with recursive Fibonacci, the way it's currently written? And the lower bound has a similar structure, but it's 2 times n minus 2. So we work that out. We assume n is even. We just make the assumption n is even, and that's fine. Okay? We don't even, well, just assume n is even, or it doesn't really matter. Whether it's even or odd, it works out more or less the same. So 2 to the 2, n minus 4. We have a 2 to the n over 2 times t of 2. So we get it down to its base case, which is either 1 or 0. I wrote a 2 here. Let me put in the 0, which is what it should be. Again, t of 1 is 1, t of 0 is 0. Well, just say it's 1 to check it. Okay? So we have this. And if it seems a little bit sloppy, it's because it doesn't have to be exact. I can be off by 1 with some of these costing aspects. Okay? So in this case, t of 0, t of 1, it costs, say, unit costs in order to check that it's at its base case. Okay? And we're left with something that is more or less 2 to the n over 2. Okay? So we've got something. That's a weird expression I put there. I'll just assume that's correct. Okay. T of n is, at most, growing like 2 to the n. But at best, the lower bound says that at best we're growing like 2 to the n over 2. That n minus 1 over 2. Just think of it as an n over 2. Okay? But another way to write 2 to the power of n over 2 is, right, if you have 2 to the, like, n divided by 2, you can take that denominator of the exponent, and that becomes a radical. So it's a 2 to the 1/2 power, all raised to the power of n. But square root of 2 is 1.414 or something. So it's still growing exponentially fast. Okay? So the idea is, even at the best case scenario for recursive Fibonacci, it's growing exponentially large. What's better, big O of n or big O of 1.4 to the power of n? Big O of n, that's much better than exponential growth. Okay? So not only are we giving an intuitive explanation for why one algorithm is more efficient than the other, we're giving at least a more formal way of noticing it and demonstrating it to, say, a colleague who questions whether or not our method is better or worse than the current one. Okay, let's look at factorial. So with factorial, this is the non-recursive factorial. So initially, maybe it costs 1 to do n equals 0, n equals 1. Okay, cost of 1 or 5 or whatever you think is reasonable, as long as you acknowledge that it's a fixed number. It is a constant. Okay, no matter what n is input, that initial stage is a fixed number. Then this loopy part, this loop is very much dependent on the size of the n that's input. And that's pretty much it. There's some constant number of operations going on here, say 3 or 5, it doesn't matter. It's still going to not affect the fact that this is a big O of n. So non-recursive factorial is big O of n. What about recursive factorial? Well, recursive factorial is a little more involved to do the costing, right? Because you do the 4-step procedure, a little more painstaking. But when you finally get down to it, it's really just big O of n as well. Okay? So recursive, non-recursive factorial are both the same big O cost. So this is now where you have a choice. Okay? So in principle, the theory is not going to give you a better choice. Okay? They're both, in theory, the same order of operations. But then at this point, you delve into a little more of the practical aspects. So for example, what is simpler to code? What's easier to look at? This recursive one or the non-recursive one? Usually the recursive one's the more elegant one to look at. It's usually much cleaner. It's like 1 or 2 lines of code. It's usually much better. Okay? What is easier to debug? Well, probably the recursive version as well, because you're literally just applying a mathematical formula in one line. You're checking a base case in another line, and maybe you're checking for out-of-bounds errors on another line. Okay? Not a lot of code there to do things. And then the final best question is, how much internal overhead is required for each? If you don't know the answer, then you just do your best guess. But in this case, what I'm going to tell you is going to kind of spoil the fun, which is every time you call a function, it slows down a little bit. There's a little bit of overhead involved in, calling the function, loading up the input parameters, loading up return values, and then exiting out of the function. There is a bit of overhead. So in general, you want to avoid function calls. Okay? So in this case, and in general, if the recursive solution and non-recursive solution give the same cost, then if code readability is the most important thing on the planet, and you have enough space for the recursion, then usually the recursive one is the better solution. If, on the other hand, you're like most people in their desire to really squeak out every last little flop that they can without too much effort, the non-recursive version is actually the better choice because there are less things that can go wrong internally. There's less overhead that is involved with just calling a loop and just updating a value in a location in memory, as opposed to actually calling a function over and over again. Okay, so the question then becomes, for merge sort or selection sort, what would you choose? You'd still choose merge sort, because even though there's overhead with the recursion, big O of n log n really is much better than big O of n squared. It really is worth the extra overhead in the recursion. Are there any questions? Okay, so I'm not going to be here on Wednesday or Friday. Professor Wallette is going to be subbing for me. And so the topics will be basically continuing on with with lecture 13. Okay, so the next topic, let me just briefly introduce it to you so you can all see it, is a search algorithm. We've done sorting. And now we're going to think about searching. These are the two fundamental things that you do with a collection of objects. Either you sort them or you search for an element. Okay? And any application you can think of, you're going to have a collection of things and you're going to want to access a particular thing. And usually the question comes in mind, how do you find that particular thing in your collection? And the answer is usually some combination of, well, if I sort everything first, it's easier to find what I'm looking for. If I don't sort everything first, then, it's still maybe not that bad. Okay? So that's the general idea here. We're going to look at very briefly about the different sorting algorithms and the different perspectives on, if you want to search for an element in a list of size 1 billion, should you sort it first and then do a search, or should you just search through blindly? Okay? So that's the topic of the search section. Okay, I will see you guys in a week.